All right, let's go to problem 3. A bored child forced to visit her parents' office in a skyscraper downtown decides to make the most of the opportunity to conduct physics experiments in the elevator. Sure. She finds that when she gives a 2.5 kilogram box of office paper an initial velocity of 3 meters per second, it slides 1.2 meters. How far will it slide, though, if she does this while the elevator is accelerating up at 2 meters per second squared? So first I'm going to draw a sketch. We are shoving a box of office paper in an elevator, watching that box slide along 1.2 meters, right? So that looks like this. Okay, I've got my elevator. I got the box. We give it an initial velocity, right? Okay, a quick shove, and it goes and comes to rest here, right? 1.2 meters later. Here the velocity is 0, right? There's some initial velocity that I'm going to give it, and it's going to slide along, come to a rest there 1.2 meters later. Okay? We know the mass of the box is 2.5 kilograms. This is going to be exciting. Okay, and so the question is, I'm going to then change things. Then I'm going to have, this is when the accelerator is at rest. The elevator is at rest, it's not accelerating. This is when the A in the y-axis is 0. Okay, clearly there's an acceleration on this box slowing it down because of friction, right? So if I did a force diagram like this, this is what it's going to look like while it's sliding across the floor, right? There'd be normal, gravity, friction, yeah? And if I did, I'm going to do it over here, sigma F equals ma. I can do that in the x-axis, and I can do a sigma F equals ma in the y-axis. In the x-axis, I'm going to have just a minus friction is mass times acceleration in the x, right? In the y, I'm going to have n minus mg is mass times acceleration in the x, but the acceleration in the y, you'd say, hey, that's going to be 0 because we are not accelerating up and down at this point. Now, what's going to happen in the second part of this problem is now we're going to have the elevator accelerating upward. And we're going to give it a shove, and we want to see how far it'll slide, okay, while the elevator is accelerating up at 2 meters per second. Okay, so same elevator. Does it look like the same elevator? I tried. Not very hard. And I'm going to give it the same initial velocity, okay? And it's going to tick, 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 and it's going to come to a rest. So the final velocity is 0. And it's going to go some distance that we're trying to find, okay? Slide along some distance. This is when the acceleration in the y-axis is 2 meters per second squared. Okay, so going up. I'm, of course, I've already kind of decided to go x and y and make upward positive, up and right positive, because I made that negative. It's going left. Okay, hey, what's my force diagram look like here? It looks exactly the same. There's a gravitational force and a normal force and a friction force. Okay, the only difference is over here, we're not accelerating up and down, so work, 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 work. But now we are accelerating up, so these forces are not balanced. The normal force is bigger while we're accelerating up. The elevator floor is pushing up into us harder to make us accelerate up. And that means since the normal force changes, that's going to change the size of the friction force, isn't it? Because friction is mu n, right? This kinetic friction while it slides. And so that means I've got a different size force. If I have the same initial and final velocities, but a different force, I'm going to have a different acceleration. It's not going to slide as far. So that's the idea here. So you're like, well, gosh, they do tell me that the initial velocity, I should have written this in, is 3 meters per second, okay? That's how fast it starts off sliding. This is 3 meters per second there. And so same thing here. This is 3 meters per second. There we go. Okay, so you say, well, gosh, I am trying to do a kinematics problem here and find that displacement, right? The kinematics problem goes like this. Let me just write out like this. A v naught v delta xt. This is usually like how I set up my kinematics problems, right? The acceleration in the horizontal direction here we're dealing with, right? These are all horizontal values. You would say, you'd say acceleration x, I don't know. My initial velocity is 3 meters per second. My final velocity is 0. Displacement for this first problem is 1.2 meters. You see, now this is going to be enough information that I could solve for the acceleration that I could then plug in here, right, if I wanted to. For some reason, sure. Okay. I feel like I'm not explaining this as clearly as I could, but I think you're good. I think you're good with this. Let's go and do the horizontal axis for this guy, and then the vertical axis for this guy. Horizontal axis is just going to be, again, it's the identical thing. Okay, it starts off the same. The vertical is going to be n minus mg, but now it's equal to m, a, and the y. All right. All righty. Sorry about that. I should have finished that before. Okay, so looking at this. Right. So over here, for this case, 3, 0. See, I don't know this distance, okay? But I recognize that I'm going to have a different, because I have a different normal force, because I'm accelerating up, I'm going to have a different friction force, and having a different friction force means a different acceleration than I had here, so I'm going to end up with a different displacement, okay? So if I tried using this mess, okay? So here we go. N is MAY plus MG. Over here, the friction is going to be minus, minus mu. N is MA in the X. Now the N here, I'm going to substitute over there. So I'm going to get a minus mu MA in the Y plus MG equals MA in the X. So do you see there's an M in every term? The mass drops out. That's convenient because well, I do know the mass of the box office paper, but I guess maybe I didn't need it. So I'm going to get that minus mu A in the Y plus G is the acceleration in the X. Okay, and that's cool. Mu doesn't have any units. A in the Y and G, this is also an acceleration. They have the same units. I'm going to get acceleration units out. It's going to work out great. So that's it. Okay, in this problem, I actually know values. They didn't tell me the value for mu, did they? So I got a problem. I need to know the value for mu, because I know this acceleration is here. Minus mu times 2 plus 9.8 equals the acceleration in the X. You're like, oh man. If I had the acceleration in the X, I would have 1, 2, 3 variables I could solve for that delta X. I got to solve for AX. Well, if I knew mu, I'd know AX. Perhaps I can get mu from this information. Do you see that? It's going to be the same surfaces, so it's the same mu. So I got to come back over here. Let's go ahead and do this. This will be minus mu n is m a in the X. Again, n is going to be mg in this case. Substitute that in there. Minus mu mg is m a in the X. Look at that. Look at that. The mass is going to just drop out again, right? Chunk, chunk. All right, so it turns out the mass of the box office paper was unnecessary information. I didn't have to tell you that. So my acceleration in the X is negative mu g. And you say, well, I don't know mu and I don't know acceleration in the X. How is this helping me? Well, here I have 3 variables. I can use kinematics to find the acceleration in the X. I'm going to use the formula that doesn't have t. That would be this one. V squared is V naught squared plus 2a times the displacement. So I'm going to find that that acceleration is V squared minus V naught squared over 2 delta x. Substitute in my values, final minus initial squared over 2 times 1.2, right? So I can get that value for acceleration if I wanted to. Do you care that I'm plugging values in now? I don't think you care. Wait, there's the calculator. So it'll be a negative 9 divided by 2.4. Okay, so that's going to be 3.75. Negative 3.75 meters per second squared is my acceleration. Okay, for this box as it slides across there. Well, now I know the acceleration. That guy can go in there, and I can figure out my value for mu. Negative mu, let's move the g over. It's going to be the acceleration in the x over g. Oh, what the heck? Let's put that negative sign over there. Why am I leaving that negative there? Okay, so mu is going to be negative, and then I put in the acceleration x, which is a negative 3.75 over 9.8. I'm going to get a mu of 0.38265. Let's just call mu 0.383. Okay. Now the mu, that value comes over here. I know mu, I know that, I can find a in the x. So I'm going to have minus 0.383 times 2 plus 9.8 is that acceleration in the x. Look, I conveniently already have that in my calculator. Times 11.8. And I get a negative 4.515. Let's call that 4.52 meters per second squared is my acceleration. Notice that acceleration, right? See, it's slowing down quicker than it did before because that floor is shoving into it harder, so the friction force is bigger. It's going to slow us down quicker. We're not going to go as far. How far are we going to go? Now that we know the acceleration, we got A, we got V naught, we got V, finding delta x. We're going to use the same formula. V squared is V naught squared plus 2A delta x. We're trying to find delta x, so that's going to be V squared minus V naught squared over 2A. That'll be 0 minus 3 squared all over 2 times this acceleration we found, negative 4.52. Still have that value in my calculator conveniently, so this is going to be negative 9 divided by the quantity 2 times, yeah, all right, it should be negative. What are you going to do? Let the negative sign out. I left that negative sign. I'm going to punch my calculator. I'm going to get 0.9966 meters. We're just going to call that 1 meter. We'll round off to that. Okay, so 1 meter is the distance it's going to travel now. Ta-da! While the elevator is accelerating up. Okay, so that's that problem. Problem 2.